Well, hello and welcome back to ENGI307, Data Analysis and Machine Learning. We're continuing our course as we're getting a nice survey of various type of machine learning strategies. And so far we've covered 3 of them. We talked about supervised learning, where we have a training sequence and we figure out how that works, so that as a result of being trained by that data, you get some new features and then can come up with an estimate of what it would actually produce as the outcome. We then talked about unsupervised or statistical learning, where we use statistical means like Bayesian theory to come up with a way of not knowing what the outputs are, but we're just trying to figure out with the statistics based on the information that we know from some set of data, we're able to come up with some results of that. Next type was a support vector machine, where we talked about using something like a kernel, where we end up doing a data transformation to try and create some separation between the feature spaces between one sample and another. And as a result of that, we can come up with some better type of learning machines. Now we're getting into this next one, where we're starting to look at neural networks. And so if any of you are familiar with neurology, with the way that the brain is working, we're trying to look at something like that, but try and come up with a model of what a neuron would be and creating networks that flow from that type of approach. So here's what we'll be covering in this module. So in terms of the general kind of outcomes, we want to be figuring out how we go about doing the generation of an artificial neuron, which is also called a perceptron. We'll be doing exploration of network architectures. We'll be looking at multi-class discrimination approaches. We'll look at training protocols, and finally, multi-class discrimination with multi-layer perceptrons, MLP networks. So what we'll have in the handful of charts here is we'll first talk about, give an introduction to what is an artificial neuron, how we would go about creating a model for that. We'll then talk about feed-forward networks. We'll talk about the error correction delta rule. Then we'll speak about error backpropagation algorithms. So we have feed-forward, and then we have backpropagation algorithms. And finally, we'll finish up with multi-class discrimination with MLP networks. So let's talk about an artificial neuron. For computers to exhibit cognitive functions such as learning, remembering, reasoning, and perceiving, which humans are known to exhibit, information must be viewed with new mathematical techniques and hardware with the ability to simulate and process cognitive information. So that's what we're trying to be doing with neural networks. The goal is a thinking computer, a truly cognitive machine. With our limited understanding of the biological process, human learning behavior emulation is possible. For an artificial neuron, neuronal information processing involves a range of complex mathematical processes and mapping functions. So here are some examples of what that might look like. And so an artificial neuron consists of a mathematical equation for calculating an output value from a set of input values. So here are a couple examples of the models. And so you have the inputs that are folding in. Those are, there's a summation with each one of those weights. And then we have another factor that we apply. And then we are able to come up with an estimate of what the output should be. Here we have an example where there's not a W0, the way that it's listed here. So a slightly different formation. So an artificial neuron does 3 things. It evaluates the input signals, determining the strength of each one. 2, it calculates a total for the combined input signals and compares that total to some threshold level. And 3, it determines what the output should be. And so there's a couple decisions and thresholding things that are going on with this type of a process. So here is a mathematical model of a neuron, also called a perceptron, as you can read about in the text. So this artificial neuron or perceptron, the input consists of here. So we have an input array of features. The connection weight vector consists of here. And so here are the weights. So the input vector, the weights, and the relationship between the input X and the output Y hat is given here. So here we have the sigma times the W transpose X plus W0, which is equal to sigma times the quantity, the summation of J equals 1 to N Wj Xj plus W0. So those are just a couple ways of representing what we're showing in these figures. And so that's the how that works. An artificial neuron includes a sigma function, which is the activation function, transfer function of the neuron. And we'll introduce a couple different types of models of what that could look like. And the weights are always adaptive. The first hidden layer may have the log sigmoid or tan sigmoid activation function as shown below. So here, the first one is we're looking at the log sigmoid activation function. And the next one is looking at the tan sigmoid activation function. So let me go ahead and pause here and we'll pick this up in just a minute. We'll continue to be talking about this.